In this video, this will be the sixth part of the Chem 111 final exam review for Purdue North Central. It's focusing on balancing chemical equations in stoichiometry. So when we balance chemical equations, we're doing it because of the conservation of matter. Which means matter can neither be created nor destroyed. Which means that things don't just disappear and appear out of nowhere. You have to account for everything that happens, for every atom that was there originally has to be there at the end. This means that everything on the left-hand side of the equation has to be the same as everything on the right. What I usually do, especially as a beginning student, you might want to write out all the chemicals we have at first, all the elements. So we have aluminum, and notice you have sulfate here. We have sulfate on the left and on the right. It still remains SO4. It didn't break down into SO2 or SO3, something like that. So I'm actually going to keep it as a set, just for simplicity. You can break it down to sulfur and oxygen if you want to, but it will make it a little bit more complicated. Then we have calcium and hydroxide. Now you go from left to right to determine how many you have of each. Here we have 2 aluminum. Here we only have 1. Sulfates, we have 3 on the left. We only have 1 on the right. If you do parentheses around this SO4, you'll notice that there's only 1 of them. Calciums, we have 1 on the left and 1 on the right. And hydroxides, we have 2 on the left and 3 on the right. So now you just keep going back and forth from left to right to get them all balanced. For instance, if we start with aluminum, we have 2 on the left, 1 on the right. So I want to multiply AlOH3 by 2. That'll give me 2 aluminums. That also changed the number of hydroxides I have. Instead of having 3 now, I have 2 times 3. So I actually have 6. That's from the coefficient 2 and 3 from what was there originally. Sulfates, we have 3 on the left. We only have 1 on the right. To balance that out, I put a 3 in front of the calcium sulfate, because 3 times 1 is 3. That also changed the number of calciums I have. I now have 3 calciums. So if I go back, aluminum is still balanced, sulfates are still balanced, so we can go on to calciums. We have 3 now on the right and only 1 on the left. So I'm going to multiply calcium hydroxide by 3. That'll give me 3 calciums. That then changed my hydroxides to 6 from 3 times 2. And that actually made the hydroxides fall into place. 9 times out of 10, that's what will happen. The last one will just fall into place. So our coefficients here are 1, 3, 2, and 3 to balance the chemical equation. Let's try another one. We have ammonium. Notice on the left we have 3 of them. On the right, we can put parentheses around it, we only have 1. The next one is phosphate. Once again, we can put parentheses around here, we only have 1. On the right, we have 2. Nickel, we have 1 nickel, and we have 3 on the right, and then we have nitrates. Nitrates, we have 2 on the left, put parentheses around these, and we only have 1. This one's going to be a little bit more complicated. Just take it one step at a time. Ammonium, we have 3 and 1, so I'm going to multiply the right-hand side by 3. That changes the ammonium to 3. That then also changes the nitrates to 3, because 3 times 1 is equal to 3. Phosphates, we have 1 on the left, 2 on the right. So I'm going to multiply the ammonium phosphate by 2. That'll give me 2 phosphates, because 2 times 1 is 2. That, in the process, messed up my ammonium. So I'm going to go back and fix that. I now have 2 times 3. I actually have 6 ammoniums now. If I go back to the right-hand side, this is no longer balanced. Instead of having a 3 there, I'm going to have to put a 6. to balance out the left-hand side. This then changes my nitrates to 6 as well, because 6 times 1, because there's a 1 out here, is 6. Now we'll go to nickels. We have 3 on the right. We only have 1 on the left. So I'm going to multiply that by 3. This changes my number of nitrates. 3 times 2 is 6. Notice once again the nitrates fall into place. So our coefficients here are 2, 3, 1, and 6. And once again, that's from the conservation of matter, that nothing's ever created nor destroyed, meaning that if it has it at the beginning, it has to happen at the end. So the different types of chemical reactions we have here, we have synthesis, and this is what you want to look for. With synthesis, you only have one thing on the right-hand side. Decomposition, you should only have one thing on the left-hand side. Single replacement, you have a compound and a single element, and then a compound and a single element. Notice what has happened here. Instead of A and B being together, now A and C together, and B is all by himself. And then the last one, double replacement, is 2 compounds. Instead of A and B together, A and C are together now, and B is now with D. So, general questions and general definitions of stoichiometry. What is stoichiometry? Stoichiometry is a way to show and use relationships in a chemical reaction. Now those relationships are shown through coefficients. They're almost like ratios. It's the big number, the whole number in front of a chemical compound in a reaction to balance it. So why do we need to balance those chemical equations? Because of the conservation of matter. What's a limiting reagent? A limiting reagent is what gets used up. There's nothing left of it when it's all done. 100% of it is gone at the very end. Whereas the excess reagent has stuff left over. There's extra of it. It's just sitting around being waiting to be used. The limiting reagent determines the theoretical yield, which is the maximum you can use, maximum that you can produce. That is something you calculate. Whereas the actual yield you don't calculate. That's if you went into the lab and you did a chemical reaction, and the amount that you weigh at the very, very end of the product, that's your actual yield. That's what you actually got produced. And then the percent yield is the comparison between that theoretical and actual. So it's the actual divided by the theoretical times 100. Alright, so let's do some practice problems with us. You have to be very, very careful when you're doing these that you're reading the question properly. No matter what, you always have to get it into moles to go from one compound to another compound in that chemical reaction. If it's not in moles, you have to figure out how to convert it to moles. We've discussed in the past 2 different sets of key terms. Grams, mass, things like that. You use the molar mass right off the periodic table and you add the numbers up. If you see atoms, ions, molecules, or formula units, you're going to use Avogadro's number, 6.022 times 10 to the 23rd. Alright, so we have 16 moles of sulfur. How many moles of iron are needed? Notice it's already in moles. So that means we can go straight to the coefficients. We don't need to convert it past that. And it's asking about moles, so that means we don't have to convert it after we're done. So this will be a really simple one. So 16 moles, 16.0 moles of S8 over 1. We have moles of S8 on the top. I want to put moles of S8 on the bottom of the next one. This is where I look at the coefficients. I have 1 in front of the S8, and I'm trying to get to the iron. I have an 8 in front of that. So 16 times 8 divided by 1, 128 moles of Fe. That was probably the most basic you'll find. Let's do another one that's a little bit more complicated. We're going to just add a little bit more each time. So we have 12.00 moles of NaClO3. How many grams of O2 are going to be produced? Now, remember, you have to go through moles in order to get there. So, we are already in moles, so we don't have to worry about that. We can go straight to the coefficients. And that will get us moles of O2. But that's not what the question was asking for. The question was asking for grams of O2. To go from moles to grams, we're going to use the molar mass. Remember, the unit grams is the key term for looking at the periodic table to add that up. So we look for oxygen, 15.999, which can be added, rounded up to 16.0. We have 2 of them. 2 times 16.0 is equal to 32.0 grams per mole. I did not do anything without its coefficients when I multiplied that out. That's a big mistake I see a lot of beginning students do. When you're looking at molar mass, do it just the way you always have. Only look at the compound itself. That coefficient is only important in that one fraction to go from moles of one to moles of the other. Alright, so we have our beginning fraction is the number we're starting with from the question itself. 12.00 moles of NaClO3. We have moles of NaClO3 in the front or in the top. We're going to have it on the bottom of the next one. Now we look at the coefficients. There's a 2 in front of there. So it would be 2 moles of NaClO3. We're going to 3 moles of O2. We're here in the chemical equation. Now we get from moles to grams. We're going to go use this, the molar mass. And we go back to 1 mole of O2 because this 32 grams is representative of just 1 mole. Moles cancel. Moles cancel. So it's going to be 12.00 times 3 divided by 2 times 32.0. That comes out to be 576.0 grams of oxygen. Because there's 4 significant figures in the first number, that's how many are going to be in the final answer. How many grams of KCl are produced? So I'm looking for grams of KCl from 2.50 grams of potassium with excess chlorine, which means we don't even need the chlorine. Alright, so remember, in order to go from one compound to another, they give us information about one compound, they're asking about us from another compound. In order to do that, we have to go through moles. So to go from grams to moles, we're going to need the molar mass of potassium. Potassium is right here, 39.098. We can round that up to 39.1. Moles to moles. Use coefficients. And then moles to grams, we're going to use, once again, we see grams there, that tells me molar mass. I need to figure out the molar mass of KCl. We know that K is 39.1. Cl is right here, 35.453, which can be rounded up to 35.5. Add those together and it becomes 74.6 grams per mole. Now we can put it into our fractions. 2.50 grams of K over 1. Grams of K on the top, put grams of K on the bottom, the next one. We're right here. We're going from grams to moles. We're going to use the molar mass. Is equal to 1 mole of K. The grams K cancel out. 1 mole K on the top, put 1 mole K on the bottom of the next one. We're going from here to here. In order to do that, we're going to use coefficients. So look for K. The 2 is in front of it. We're going to KCl. 2 moles KCl. The moles of potassium cancel out. We are here now, and we're trying to get to grams of KCl. So in 1 mole of KCl, there are 74.6 grams KCl. So 2.50 divided by 39.1 times 2 divided by 2 times 74.6 comes out to be 4.77 grams KCl. We're going to do one more problem where we try to determine the limiting reagent now. The reaction of 4.25 grams of chlorine and 2.20 grams of phosphorus produces 4.28 grams of PCl5. What's the percent yield? Well, they're giving you the answer here. This is the actual. So what they're wanting you to do is figure out the theoretical yield and figure out how much percentage there is that they got out of what they should have gotten. Notice that they gave you two numbers on the left-hand side. They gave you 2.20 and 4.25. You're going to have to convert both of those over to grams of PCl5 because you're going to have to compare them. Whatever smallest is going to be your actual theoretical yield. Whichever one was bigger is excess reagent, and you have more left over. You have excess of that. Look at this as two different stoichiometry problems in one. So you're going to do stoichiometry with the P4, and then stoichiometry with the Cl2, and then compare the two answers. So we'll start with the phosphorus. In order to go from one compound to another, we have to go through moles. So I need to convert this over to moles first. In order to go from grams to moles of P4, I need to figure out the molar mass. So I look at phosphorus, 30.974. I have 4 of them here, so I'm going to multiply that by 4. That comes out to be 123.896. Once we get into moles, then we can go moles to moles using the coefficients. And then go moles to grams by looking at the molar mass of PCl5. Because grams, that's why we need to know the molar mass. So by looking on the periodic table, P is 30.974, and I have 1 of them. And chlorine, I have 5 of them. And I look at chlorine, and I see 35.453. Multiply that out. And 5 times 35.45 is 177.45. And then you're going to add them together. And that comes out to be 208.224. grams is equal to 1 mole. So I'm going to do the entire stoichiometry with just looking at the phosphorus first. I'm going to discard the chlorine for now, and I'm going to come back to it once I get a number here. So I have 2.20 grams of P4 over 1. The molar mass of P4 is 123.896 grams in 1 mole. I'm right here now in my picture, in my plan. Now I need to look at the coefficients. P4 has an invisible 1 there. PCl5 has a 4. Now from here I can figure out how many grams of PCl5 there are by looking at the molar mass. So in 1 mole of PCl5 there are 208.224 grams. So 2.20 divided by 123.896 times 4 divided by 1 times 208.224. That comes out to be 14.79 grams. Now we're going to do the exact same question, except we're going to be focusing on chlorine this time. So we're starting off with 4.25 grams of chlorine, and we're trying to figure out how many grams of PCl5. So I see grams. In order to get to moles, I need to look at the molar mass of Cl2. When I look at the periodic table, it's 35.453. Wrong way. Or 35.5. 45. Times 2 is 70.9. Moles to moles, we use the coefficients. And then moles to grams, we're going to use the molar mass. We already calculated the molar mass in the last question. It's 208.224. Now we're going to set up the stoichiometry. So we have 4.25 grams Cl2 over 1. We have grams of Cl2 on the top, so I'm going to put grams of Cl2 on the bottom of the next one. 70.9 is the molar mass off the periodic table. 1 mole Cl2 is on the top, because 70.9 grams is equal to 1 mole. We have moles of Cl2 on the top. That means I need to put the moles of Cl2 on the bottom of the next one. I'm right here in my plan to go from here to here. I need to use the coefficients. The number 10 is in front of Cl2. Then we have 4 in front of PCl5. Then for every 1 mole of PCl5, I have 208.224 grams. So that's going to be 4.25 divided by 70.9 times 4 divided by 10 times 208.224. That comes out to be 4.9927 grams. Or just 4.99 because of significant figures. There's only 3 here. Now if we compare the two numbers, 14.79 versus 4.99, 4.99 is smaller. That's going to be our theoretical yield because it's the smaller. That means that Cl2 is our limiting reagent, which means P4 must have been our excess reagent. So by determining this, we can figure out a lot of things all at once. So the percent yield is going to be the actual over the theoretical times 100. So the actual is 4.28 The theoretical is 4.99 times 100. That comes out to be 85.8%. And that's how you do percent yield. And that is the 6th review for this exam.